Hello everybody and welcome to the Carl and Cymru revision sessions. The session this evening will focus on 4.8 organic synthesis and analysis and will be presented by Mrs. Stevens from e-sgol Bropeda. The session will last around 45 minutes where Mrs. Stevens will run through the relevant content focusing on exam technique. If you have any questions during the session, please use the question and answer section and we'll do our best to answer you. You will see that there's a hyperlink in the Q&A section. If you have to leave your name and email address, we'd love to keep in touch with you so that we can send you information about future events. You can click on the link at any time during the session. Today's session will be recorded, and the recording and any event resources will be uploaded to the e-sgol website under the Carl and Cymru tab. So thank you, Ms. Stevens, and over to you.
Good evening to you all. So as that first slide suggests, I'm just going to quickly cover the organic synthesis and the analysis section of Unit 4. Now, there's a very good reason, and if you've been joining us for the previous few sessions, you'll know that we are pretty much being led by the advanced information that's been provided by the WJC this year. And as you can see, the highest ranking one this summer will indeed for you be that section 4.8 on organic synthesis and analysis. So that's why we are going to go through that with you primarily this evening. Okay, so the spec, I'm sure you're all familiar with it. Hopefully that you are significantly through your organic content already. Possibly not that 4.8 because obviously it is that final unit for the majority of you. But you would have touched upon lots of the content already. And don't forget about the synoptic element that you have between year 12 and year 13. So lots of these techniques themselves have indeed been covered somewhat in year 12, of course, in that unit 2 you did last year. And talking of that, it's probably useful to tell you now, I'm not going to be focusing on the techniques in any sort of depth this evening. Okay, and the reason is because there has been a session prepared for you from, I think it was spring 2022. So about 12 months ago, I did a session that went into quite a lot of detail about the techniques like infrared and mass spec and NMR, etc. So to give this session a bit more kind of direction and different to previous sessions, I'm going to stick to how you approach questions, so exam technique more specifically than the techniques themselves. Okay, but please, if you're unsure of any of the content of the techniques, that session on the Catalan site is well worth it if you need clarity in anything itself. Okay, right, so organic synthesis. Now, organic synthesis as a term, okay, simply means that we need you to thinking about how you can prepare the organic families that you're familiar with. Now, there is an array of organic families that you have touched upon, built upon quite massive in year 13 compared to year 12 then, where we've introduced that nitrogen chemistry as well, not just the carbon-based one. So many industrial processes involve multi-stage processes as well, and that is something that is well worth keeping sight of as well, touching upon that 2.3 green chemistry and things like yield and atom economy. Okay, that also feeds into this 4.8 and why organic in particular is a bit of a rubbish area, and synthesis is often quite poor yield, or on the other side, it can also be quite poor atom economy as well. So that's just dragging in that synoptic element from year 12, because we don't really touch upon that much of yields and atom economy as a spec content in year 13, but please do not lose sight of it, okay? So when any kind of chemist plans a synthetic route, they have to consider lots of things, obviously. But it's things like, are the reagents required to convert from one functional group into another? What is that reagent? Is there the presence of any other functional groups in case they also react and you don't want them to react? What conditions are needed? Temperature, pressure, catalyst. That kind of drags in the Le Chatelier principle then, and equilibria, of course. Rates. So obviously you've revisited rates already this year. So what effect does the rate have on what synthetic route you decide to choose? So, and I've touched on things like that, like the yield, the atom economy, the safety, whether the byproducts are safe for disposal or easy disposal or not. And obviously industry is led by money, of course, and the financial economy of it. So there are lots and lots of considerations when chemists choose what route they take, because it's not always the one that is direct that's chosen. Okay, so common kind of functional groups that you find in organic molecules, you've got the alkene, the hydroxyl or the alcohol families, halogenoalkanes, carbonyls, amines, a lot. Hopefully now you're a bit more familiar with at least identifying what organic compound class you are dealing with. Okay, but this is what we need to really get to the crux of, is that organic synthesis fundamentally is all about getting from the starter material to the target material or the target molecule you want to get to. And often there is a direct route, but there's often an alternative route between not a byproduct then, but an initial product that you then transfer further. So organic synthesis is often about trying to get that balance between, right, if the direct route requires quite a lot of energy maybe, or high temperature, or the pressure is unfavorable, is there an alternative way we can get to that target molecule by going to something first and then converting and reacting that? So I suppose esterification is a classic example of that, where you can esterify directly an acid and an alcohol, of course, but that reaction is a reversible one. Whereas if you first transfer that the acid into an acid halide, let's say, and then you esterify the acid halide, then the yield is much, much greater. So it's about getting your heads around what the organic synthesis route is most favourable, I suppose. Okay, so that's just a list of all the functional groups that you need to be familiar with, really. Any of them are not familiar to you, then please ask a question in that QA section, but most of these are built upon from year 12, and as I said, we've dragged in that nitrogen content from this year as well. Right, so there's lots of different kind of routes, and this is something I suppose I should advise you on. Don't feel free to ignore it, but I often tell my pupils to have a master piece of paper, and as you are going through the content itself, as is being taught, maybe, if possible, if you're still at that stage, but certainly when you get into the revision, it's advisable to have this kind of large piece of paper that you then write, okay, I've got an alkene here, how do I get from an alkene to a ketone or whatever? So it's good to build as each little subtopic is taught you, so that you get a big picture, literally a big picture, big piece of kind of mind map. I suppose it looks similar to going this to this to this. It's well worth having it. Okay, so this is one I stole from my own kids. Okay, I think it was a good few years ago back. Now I had a pupil that literally did this for me, and I've kept it. I said, do you mind if I keep a copy? And I keep giving this to my pupils. So he put in the reagents, he puts in the conditions, etc. And it's really well worth having one of these master plan, I suppose, of interconversions and what can convert into what and what route and what order. Okay, so that is a really good tip for you, is to start that as early as you possibly can. Okay, right, so thinking about this kind of exam technique, let's hone in on a kind of class of question that you often have, which is, how do you differentiate between certain organic compounds? It's a very common sort of question that comes up. Okay, so as I said, lots of these have been taught in AS, but in A2, you've obviously built upon that massively. So how could you distinguish between any sort of classic compounds by simple tests? Okay, so this is just quickly reviewing the test for you. The test for an alkene. So alkenes, if I take first off what you did for your Key Stage 4 studies, the test for an unsaturated system was bromine water decolorizing. And in year 12, you also had that synoptic element that could potentially be dragged in for year 13. We also introduced you the second test for an alkene, which is that you can identify using potassium manganate. Okay, and that will also decolorize. So there are two tests for an alkene that you should be familiar with, building on your Key Stage 4 studies, but also dragging in what was covered in year 12, which is that secondary test, which is using permanganate. Okay,
Mrs. Stevens, could I just ask a question for a pupil?
Yeah, go ahead.
They're just wondering, do they actually have to know both tests, or is it okay just to quote one test? I think they're particularly familiar with the bromine test.
Yeah, and do you know what? I'm all for going with what you're familiar with. Okay, so I only mentioned both there because if you felt that you needed to say both, it doesn't. If you're more happy remembering the manganate, because some of my pupils say that's familiar to me because it's an oxidizing agent, Miss, do I need to learn both? No, learn what's familiar and what's most happy to you. Most would probably lean towards the bromine water because that's what they learned in year 11. Okay, but
Thank
certainly
you.
you don't need both.
Okay, great.
Okay.
Thank you.
Right, so test for halogen-alkanes. This again is something you're familiar with. I'm not going to go and read through these tests for you because you'll be able to stop, pause, jot down anything you're not happy with or unfamiliar with and build upon it. So I'm just going to quickly skim through them for you. So aldehydes, you've come across hopefully not only on paper, but you've had physical testing yourself. I'm hoping you've had your hands on to do the tolerance test in the lab, hopefully, or failings. It is the tolerance test that's often examined because it used to be the one that used to be in the Unit 5 practical test, is that they gave you reagents for tolerance. They rarely gave you the failings test in the practical Unit 5 exams. So I tend to make sure that my own pupils are very familiar and hands-on with the tolerance test. It's a particularly tricky one to carry out as well. So test for aldehydes you're familiar with. Carboxylic acids kind of builds on key stage 4 again there when you know about the carbonate test, acid chlorides, or any acid halide really. So all of these I'm not going to dwell on, but feel free to stop the PowerPoint afterwards and then carry on when you have jotted down anything you're not familiar with. Okay. So all of these are expected for you, okay? Now, it's possible to make a large number of organic products from very few starting compounds, and you need to know, and this is the key thing, they're very, very keen on you knowing what reagents are needed and the conditions required, okay? So again, I'm going to run through them, but not dwelling on any of the content in particular, because you can do that at your leisure after this evening, okay? So you need to be familiar with you need to be familiar with the alkane to the chloralkane. Now that's classically the photochlorination. So it's the homolytic fission, etc. So you need to be familiar with that. Chloralkane to an alcohol, chloralkane to an alkene. There are lots of these reagents you need to be familiar with. So they're numerous. Do not get scared by them, okay? And that's when I go through these with my own pupils, they tend to have that kind of very panicked look suddenly when they think, oh my God, my son needs to learn all of them. Well, in reality, yes, you do. But please keep in sight that lots of these are the same classification. So lots of these are nucleophilic substitutions, and the mechanisms of which will therefore be very, very similar. So don't go turning into a panic mode of thinking, oh my God, I'm never going to remember that many, because the number will scare you. If you write down every single reaction you might possibly be asked, it is scary, but you can duplicate, or at least duplicate the mechanism for many of these. If they're, for example, electrophilic addition or nucleophilic substitution, it's the same mechanism, okay? So not dwelling on them, I'd like you just to go through them at your leisure, okay? But there are lots and lots and lots of them, okay? So I'm going to focus more on the questions themselves. And you can see here that I've got classically two compounds, R and S. And how would you go about with a very simple test tube side of a reaction? So I'm not looking for anything complicated. I'm not asking you to analyze it with expensive apparatus like HNMR or infrared. How would you, simple, distinguish between these? Well, what you need to focus on is what is the difference between them. So the secret to answering these is identify what compounds you have. So what we have in this case is a primary and a tertiary alcohol. So you've got a primary alcohol here, okay, and you've got a tertiary alcohol there. So, right, do I know of any test that can distinguish between them? So the question might be better is, will one of them do one of the reactions and the other one won't? Well, the reality is you can oxidize a primary as well as a secondary, don't forget, okay, alcohol into a carbonyl, so an aldehyde or a ketone, but you can also further oxidize it into a carboxylic acid if it's primary. But the key thing to focus on here is that you can't do it for a tertiary, okay? So the approach would be, like, let's try oxidizing it then. So the possible answer would be using the two, and don't forget you do have two oxidizing agents you're meant to be familiar with. Both would be carried out in acidic conditions. But you've got potassium dichromate there, or you've got potassium manganate 7. Okay. I tend to tell my pupils to try, if it's not too much crowding of their brain space, is try learn both of these. Okay. But if you're going to prioritize one over the other, I would say this is probably the one that most of my pupils lean towards. Okay, so if you have the oxidizing agent of dichromate, then we know that it starts orange and it will end up being green. Okay, if you have the potassium manganate 7, it starts purple and it will decolorize. Okay, it is worth noting here, you have to get the colors correct. Okay, you don't get credit if you at any point give an incorrect or inaccurate color change, so keep an eye on that one. Okay, the other classic mistake is, and if I go back to why I worded the question, they often put this, which is if they're tested separately with a reagent, okay, do not forget to refer to both possibilities. So it's not good enough to simply say that R would go from orange to green with dichromate and then stop. You have to mention this detail, which is that S, which is a tertiary alcohol, in fact will have no observable reaction. You don't see anything happening. Okay, right. Before I go on to the next one, I'm going to just quickly reassure some of you that might be panicked. Lucas test is something I teach my own pupils. It's not, in fact, something that is specified on the WJC spec itself. So you don't need to be familiar with the Lucas test. So if you don't know what that means, do not panic. Okay, my own pupils will, hopefully, if they've tuned in this evening, but don't panic. Okay, it's not on the WJC syllabus. Okay, so another sort of question that you could ask. Oh, it has gone on strike. Right, there you go. Describe how you can distinguish between the compounds in the following pairs using one simple test. So it's the same question, okay, but this time we've got an ester. Okay, so as I said, first step here, identify your organic family. What are you looking at? So you're looking at an ester there, and that is a carboxylic acid. Okay, well, hopefully you can build upon what you're already familiar with from GCSE, which is, you know, the test for an acid is adding a carbonate. Okay, that hasn't changed in year 12 and year 13, because carboxylic acids, even though they're not strong acids like the mineral acids HCl, H2SO4, etc., they are strong enough to give a positive test to the carbonate test. So their acidity is enough to give a positive. So again, I wouldn't deviate too far away from that. So you've got the addition of a carbonate or hydrogen carbonate more commonly in A level, I suppose. Okay, with T, the ester, you'd have no observation, but obviously the U, the carboxylic acid, you'd get effervescence of CO2 given off. Okay, now it is worth noting that carboxylic acids will in fact also evolve hydrogen, so the MASH one from GCSE, I suppose, where the metal and the acid, but it's not very convincing. So I would say this one is probably one to steer slightly away from. But if you're sitting there in the exam and you can't think of any other test, then maybe lean towards that one is better than nothing. Okay, you can also use an indicator, I suppose, because we know that the pH of esters and acids are different. Okay, so you'd get, if you looked at litmus, for example, blue litmus would go red in U, the acid, but the ester will not prove acidic to turn the colour change from blue to red. So that is a possibility as well. Okay, right. What you got there then, the third type of differentiation we've got there, well, what you've got is a ketone. So they're both carbonyls in this case, but you've got a ketone on this side, and what you have this side is an aldehyde. Now, I've already shown you and touched upon this a few minutes ago, where I said that an aldehyde, I hope you've had hands-on experience of identifying these in the lab. I'm hoping you've got into those lab books of yours and been allowed access to these chemicals. And the aldehyde test my pupils have practiced in the lab is the one for tolerance. Now, you can use failings as well, but my own pupils have not been let loose on the failings test, but they have been let loose on the tolerance. So it doesn't matter which one you choose. In theory, So in this type of question answer approach, I would say both are just as valid as each other. Okay, so you got the ketone, you got the aldehyde. This is the one I would lean towards. But touching upon what we'd said earlier, we know that oxidizing agents will oxidize the primary to a aldehyde and further oxidize that to a carboxylic acid, whereas the secondary alcohol, which is the starting material for the ketone, cannot be further oxidized. So if you use the oxidizing agents as the color change again, an aldehyde will prove a different color change, whereas the ketone is as oxidized as it will be and therefore will have no observation. That's what the root of that test would be there. Okay. So hopefully that has given you a kind of insight of some of the lower marked questions, which is classically, how would you come up with a very quick, rapid test between A and B? How would you differentiate between them? The remainder of this session, I'm going to focus on what often scares the living daylights out of my pupils, which are those very chunky, you might not have seen them yet, questions near the end of organic papers. So Unit 4 papers often have an 8 to 10 mark question, which, don't forget, is around 10% of your entire paper on one question. Okay, and they are tricky in the sense that you have to, if possible, use every bit of evidence that they present you. So, for example, this question came up a few years ago where they gave you the qualitative analysis. So they told you the percentages of each of the elements. They then told you the mass spectra evidence was as this. Then they gave you some chemical tests that then further can be used to build a bigger picture. Is all about, and this is what is tricky and what often catches people out, is that you have to not only prove that it's something, but occasionally you have to disprove something else. So it says here at the end, explain why any other possibility isn't a possibility. Okay, so don't lose sight of the entirety of the question. Cruel as it may seem, identifying the correct product often is as little as 2 out of 8 I've seen in the past. Okay, it's the explaining and disproving other possibilities along the way that you need to focus on. So what I've done here, I've taken the same question, but I've broken it down into sections for you. And I'm going to take each bit of evidence in order and then tell you the approach I would suggest you take. Okay, so it says here in yellow, qualitative analysis. I suppose it's also a good tip to tell you, it tends to be best to take the evidence in the order they've worded it. So if you go back to the question, this is where you start. Don't start going rogue on me and start with that piece of evidence. Yes, it does come in useful, but build, okay? Start from the beginning and work your way through. So I'm going to start on that yellow there, which is the qualitative analysis. All of you should be hopefully really, really confident in qualitative analysis and how you work out empirical formula. Hopefully, okay? So from that yellow evidence, okay, first thing to note, they didn't tell you how much was chlorine, okay? They just said the remaining percentage, but it's percentage. So we know, as I show you here, hopefully, okay, is that you have the percentage of chlorine is 100. Take away how much you had for the other two. So it told you 32.47% carbon, and it told you 3.63 hydrogen. So first thing, work out how much chlorine you have. So this is the classic layout, and I would really, really strongly advise you do not deviate away too much from this classic layout, okay? Is that I would then work out the percentage divided by the AR. So in this case, 32.47 divided by 12, etc. You can see, working your way through. And this is the one my pupils often need reminding for. Once you've worked out the percentage divided by the AR, divide by the smallest answer you've got. So if you notice, this was the smallest answer I got, which is why you'll notice I'm dividing all of them by these, okay? So the ratio comes out to be 3 to 4 to 2. So that is my empirical. I've used that evidence. I've got myself a few marks clocked on, okay? The next piece of evidence was that it said in the mass spectra that it contained the 2 chlorines. Now, because I'd worked out the empirical was C3H4Cl2, that also tells you that it's the molecular formula as well. Because if the mass spec proves that it's only got 2 chlorines, There is no possibility of scaling that up to, let's say, C6H8Cl4. It's told you in the mass spectra. There are only two, okay? So the other bit I need to focus on then, okay, is that from that molecular formula, you can see that it meets the criteria of classically from GCSE, CN, H2N. That's it. So if you look at it, C3, and you've got 4 plus 2, so you're looking at the doubling. So it's not doubling plus 2, which is the alkane generic formula. You're looking at the fact that that proves to you that it's unsaturated. It has to contain a double bond between two carbons. Okay, this extends itself to lots of possibilities. So we aren't limiting itself to 1 or 2 at the moment. Okay, because those chlorines could be on any of those 3 carbons. Okay, but it does tell you that it's unsaturated, so 2 of those carbons must be double bonded. This is also, if I go back to the question, is further confirmed by the fact that it did tell you that it decolorizes bromine water, which probably, going back to the question that was asked earlier, possibly the most commonly used test for an alkene is indeed that bromine water from the examiner's point of view as well. Okay, right. So we've got the molecular formula extend itself to lots of possibilities, but, okay, the mass spectra also told you that there was a methyl. Now, as soon as you take a methyl off the formula C3H4Cl2, you're down to only 2 possibilities, okay? You're down to the possibility of having both the chlorines on the same carbon, which is the unsaturated carbon, or it's 1 on each of the unsaturated carbons. There's only 2 possibilities left. Okay, so these are the 2 possibilities. It could either be 1,2 dichloropropionene, or it could be 1,1, having it both at the same terminal, I suppose, carbon of that chain. Okay, so those are the 2 possibilities. So how do we go about then deciding which of these 2 possibilities we have? Well, it did tell you then that when compound Q reacts with hydrogen, the compound produced has a chiral center. And I'm hoping you all know what a chiral center is. So chiral center, by definition, is a central carbon with 4 different things attached to it. Okay, so this product, if you saturate the first possibility, which was that A, okay, if you saturate that with hydrogenation, then you end up with this compound. Is that a chiral center? Well, no, because I've got 2 carbons attached. Is this the chiral center? Well, yeah, in fact it is, because I've got a methyl, I've got a chlorine, I've got a hydrogen, and I've got what initially might look like a methyl, but it's not because of this presence here. Okay, so that is indeed a chiral center. Okay, whereas if you look at the hydrogenation product of B, you'll end up with this one. And that one isn't a chiral center because it's got 3 hydrogens. This one isn't chiral either because it's got 2 hydrogens and 2 hydrogens is what this allows it. And this one's got 2 chlorines. So that again is not chiral. So that confirms, therefore, at the end of that, that because it's got a chiral center, that the product must have been that of hydrogenation of A. So Q is in fact therefore 1,2 dichloropropionene. Now that is a lot of work and I appreciate that, okay? But if you go back to it, I think from memory it was worth a good, yeah, it was worth 8 marks, okay? So it means that the examiner all along intended you to spend around 10 minutes on that question as a minimum, I would say, okay? So advice, work through it step by step. Do not get tempted by going for something rogue at the end of the evidence as the starting point of your answer. It's not going to work, okay? Fair dues to the WJC, they do tend to present the evidence in the order they want you to deal with it, okay? Another past paper question, 2 marks, okay? It says there about the NMR. Now, it is worth noting here that it is a high resolution one that they're looking for because it asks you to relate to the splitting pattern, okay? But it also asks you about the relative peak. Now, in year 12, you'd only really develop the low resolution HNMR. Hopefully, if not done yet, don't panic, okay? But I'm sure a number of you have already also gone and developed that into the high resolution NMR, which means that you need to be looking at the neighbouring proton environments as well. So for A, if you look at A, first off, what is the peak area? Well, there's only one of that type, okay? Now, splitting pattern takes on board how many protons are on the neighbouring carbons. If you look at A, the neighbouring carbon is this one. Well, it's got none. It's got none of them, okay? So the splitting pattern rule is however many there are on the neighbouring carbon plus 1. So being that the neighbouring is a 0, do not forget the plus 1. The splitting pattern would be a singlet. In the same sense, if you look at this one, the only difference in this case is that there are 2 of that type. So the relative peak area ratio would be 2 this time. But again, if you look at what's neighbouring it, it's neighbouring the same one again. It's got no protons on the neighbouring carbon. And therefore, again, it would indeed be a singlet. Okay, so I'll put in there the mark scheme, and I won't get to the end of the PowerPoint this evening. That was to a certain degree my intention, just in case I spoke too fast, I'd have enough for you. But also, I think it's really beneficial to see as big a range of these type of analysis questions as is possible. Okay, this was another chunky one, and if you look at it, I think it was worth 10 marks for this one. 10 marks for one question. It wasn't even the entire question, it was only section A. So let's go back to the evidence again. They like this type of approach. They start with a quantitative analysis requirement again. Okay, so it's found to contain 53.3% carbon, 11.1% hydrogen by mass. But it did tell you that it contains carbon, hydrogen and oxygen. So again, you're going to have to do a very quick calculation of the percentage to work out how much oxygen you have, because it ain't been told. Okay. The second thing is that they've introduced you to the mass spectra. Now, before you go any further on mass spectra, you need to focus on this one. This is what is called the molecular peak. Okay. Now, the molecular peak, use my writing, but it's more clear. There's the examiner's mark scheme coming up as well. But the molecular peak will tell you, therefore, the mass of the entire molecule itself. Okay. It is also worth taking note of anything else. Now, there are 2 approaches to mass spectra, and I differ from my own colleague here in how he teaches it. He teaches it to try and identify each peak as what it could be. I tend to teach it as look at the molecular peak and look at how much has been taken down off of it. So I would have focused on the fact that dropping from 90 to this, and that is actually 75 if you look at the scale, is a drop of 15. Now, 15 is a classic molecular peak for a methyl. So that is a very strong suggestion that you might indeed have CH3 plus present, which would weigh 15. Okay. Before I go on any further, because I haven't said it, I do say on the earlier clip from last spring, do not forget to put a positive charge on your peaks. Okay. The mass spectra are all positively charged fragments. Okay, so you cannot omit this. This is not optional, it is necessary. Do not forget it. The other thing I would focus on in this, that is a peak of 17. Okay, and so it identifies lots of interesting things. Okay, right. Then it introduced the infrared. Now, infrared, I would tell my pupils, you need to really focus on 2, which doesn't require you to look at the data sheet. Not that the data sheet is ever going to be taken away from you, but there are 2 peaks I would suggest you kind of chisel onto your memory, which is a region of around 3,300. That is indicative of OH. That is one I tell my pupils, just have it on memory. And the other one I tell my pupils to have on memory is in the region of 1,750, which is indicative of a C-double bond dome. Okay. The rest of them, I would say, rely heavily on that data sheet. But if you see these, it is pretty good indicator. Okay. So going through the data and the evidence presented to you bit by bit, the first thing that it needed you to do was do that quantitative again. So it says here you got certain percentage of carbon, certain percentage of hydrogen, First thing to do, work out how much oxygen you have. Okay, well, percentage of oxygen by that maths was this figure there. Okay, then following the same procedure as I did earlier for you. Okay, do the percentage divided by the AER, and it comes out of these. Now, some of you might look at numbers and your certain brains suit numbers better than others. Don't be discouraged if your brain isn't of that type. Some of you might automatically see the fact that that is a ratio 4:10:2. Okay, if that is not clear, then the approach I would do is, as I said earlier, divide by the smallest. Okay, so you would divide 4.44 by 2.22, 11.1 by 2.22, and that would actually give you the empirical formula in the ratio you want, which is C2H5O. If you do spot this, and possibly that's where it comes back and bites a few mathematical brain pupils, is if you put down, but because you see the pattern as 4:10:2 and leave it, you in fact lose marks because they're looking for this, which is an empirical, and they're looking for the lowest ratio possible. So don't forget to convert down to the smallest ratio possible. Otherwise, you are losing marks that are not needed to be lost. Okay, so lowest ratio, as I said, I would focus on the fact that you've got certain peaks. So that is 90, that tells you it's molecular. If I go back to empirical, that has a mass of 45. Okay, 2 carbons, 5 hydrogens, and an oxygen has a molecular mass of 45. Okay, so suddenly that 90 becomes significant because it's telling you that the molecular is twice that empirical. Okay, it's also worthwhile, as I noted earlier, noticing the fact that you've got a drop of 15, indicative therefore is suggesting I have a methyl present. Okay, so you got the mass spectra there, which is 90. That confirms double the empirical to get the molecular formula. It says that you needed also to refer to any other fragment. But it says here fragment. So, for example, I would have said that the 15 one is likely to be down to that methyl. Don't forget the positive charge. Okay, so don't just focus on the molecular peak. Mention a few others if you can. Okay, infrared. I did tell you, I tell my pupils to memorize 2 particular ones. Interestingly, what you notice immediately is that is in the region of that 3,300. So that is telling me I have an OH present here. Okay. Sometimes the lack of evidence is the best type of evidence, because what you notice is that you do not have a peak. Sorry, here's what I needed to. Apologies. I just get rid of that before it confuses anybody. Okay. We do not have, okay, a peak in the region of 1,750, which tells you we do not have that. It's discounting the presence of that C0 Vondo because we don't have it. Okay. Right. IR, therefore, it confirms that you have an OH peak and nothing else of significant. I do touch upon it in the clip from last spring, okay, but this is what we call the fingerprint region. It is very, very similar to most organic compounds, so it's not really indicative of anything. It doesn't really help, if I was honest, okay. So anything above the fingerprint region is what you're focusing on. So this is what we call the fingerprint because it's standard to just organic compounds, okay. So the IR is only useful to confirm the presence of the OH, but the absence of the C Vondo is significant in itself because of the fact you know that you've got the empirical with oxygens present. So is it a double bond O? Is it an OH? Okay. Low resolution NMR only had 3 peaks. So we're going back now to year 12 NMR really, which is how many different types of hydrogen do we have? Okay. Well, the fact that there are 3 environments tell you that there would be 3 types of environments. Okay, now I'm going to come back to that in a minute. I'm going to come back to this very slide because so far, yes, I've identified the 3 environments, but it's not really going to help me until I get one further bit of evidence under my belt, which is the fact that it told you then the next piece of evidence they introduced was that acidified potassium dichromate, there is a color change. Okay, that tells you that we are dealing with either a primary alcohol, a secondary alcohol, or an aldehyde. Those are the only 3 organic compounds, families then, that will give a colour change with an oxidizing agent. Okay. It interestingly though then tells you that the product does not prove positive to the acid test. It doesn't react with aqueous sodium carbonate. So that tells you of the 3 possibilities, primary alcohol would oxidize all the way to a carboxylic acid, and aldehyde would oxidize all the way to a carboxylic acid. So the only option then is a secondary alcohol to make a ketone. That's the only option we have open to us. Okay. So that tells us that we are now very much dealing with a secondary alcohol because of the fact that it did not test positive to the acid test. Okay, so the sodium carbonate. So based upon that, we know that we are dealing with hydroxy groups. So we're probably dealing with a diol. The question is then, am I dealing with a diol of terminal, so are they at the end, or are they both central? Okay, so I'm going to go back a few slides to where it told you that the low resolution NMR had 3 environments. So there are only 2 options left. It's a diol. So the 2 options we have is having them, excuse me, I'm going to be really lazy to a certain extent, and I'm just going to put dashes in if it signifies just a hydrogen. Okay. That's one possibility. The other possibility we have is that if we have them on the second one. Okay, so we have one on one end and one on, sorry, the same one. Okay, so to focus on the fact that we know that it is a secondary alcohol, it's not tertiary, it's not primary, okay, we've got a choice of having the OHs on position 2 and 3, or we have them on position, both on the same one, so position 2 in this sense. Well, then you need to focus on the fact, how many environments am I looking at? Well, in reality, what you're looking at is you've got one environment here, which should be identical to that one, so that's one environment, okay. You've got another environment then, which is this, and then you've got one environment that it be this one. So that would be 3 peaks we're looking at, okay? Alternatively, if I look at this one, I've got one environment there, happy days, that's okay. I've got one environment here, okay? We've got one different environment then, which is that one terminally. But interestingly, and most crucially, you've got a 4th environment if that is the possibilities. Okay, so we had to have a secondary, but if you look at it, I've now got 4, or I'd expect 4 peaks for the NMR of the 2,2 diol, whereas if you look at the 2,3 diol, it would only present 3 environments because it is symmetrical down the side there in the middle. Okay. So putting all of that evidence together, all the evidence in order, we established had a molecular formula of C4H10. We established that it had a molecular mass of 90, okay? Also established it had a methyl because there was a fragment of 15. IR confirmed the presence of hydroxy, but not of a carbonyl. Okay, so we know we got OH. We know we got 3 environments. We know it has to be secondary because it did not prove positive to the sodium carbonate. All that together tells you that it is butane 2,3 diol. So again, I appreciate it sounds like, and it felt possibly like a lot of work, but they were giving you 10 marks for that answer. So you have to earn them, okay? Right, how much time have I got left, peeps? I've got literally coming down to the last few minutes, okay? So that was one. I did put down as well, just as a little reminder, just because I like throwing in odd facts here and there. Do not lose focus on the fact this is actually a chiral compound again. Okay, you've got a chiral center right there. Actually, you've got another one there, but it's chiral in 2 positions because of the mirror image that you've got possible for this organic compound. Okay, right. Say the type of reaction that occurs when X is warmed. with acidified potassium dichromate. I've said it quite a few times. It's an oxidizing agent, so it's oxidation. Okay. Draw the structure of the organic product formed when X reacts with acidified potassium dichromate. Well, that is what we identified X to be. If it's oxidizing, it's going to oxidize both of them. Okay, that's the crucial thing. So the three definitions of oxidation is either gain of oxygen, loss of hydrogen, or the loss of electrons. In this case, what it's going to do is knock off those hydrogens and turn it into a dione. Okay, so you've got a ketone on two separate positions there. Okay. It is worth noting they're not all cruel all the time. There would be error carried forward. So if you'd identified X inaccurately, they would have marked this one as a consequential mark. Okay. So this is another question, and I will leave you to browse this at your leisure, but it's another interesting one because it was a bit of a head scratcher in the sense they gave you 6 compounds and said, which ones could you identify with just infrared alone? 4 of which you can, 2 of which you can't. So I'm hoping you can spot certain characteristics about some of these compounds that are present for some but not on others. Okay, for example, we've got an OH. It's the only one with OH in there, so that would be a tick for that one. So it's training your brain to look for something that is only present in one. Okay, so you'll notice that there's a bromo in 2 of them, but if you compare C and D, okay, this one has a bromo but does not have this. Okay, so that one have 2 distinct IR peaks, the halogen, the BR, but also have the unsaturated C1C, give another peak. And in that sense, that would only be the bromo. This one would just be the C1C, wouldn't it? So those are the 4 that you could identify solely with IR. Okay, being E can't be used that way, so it'd be a case of coming up with another instrumental analysis method. Probably in this case I would have lent towards NMR. Okay, so at your leisure after the session, please take the time to go through the rest of the questions that I put up there. This one quickly show you this one because I like it, if I was honest with you. It's one that I give my pupils every year. If you got A, what is B, what is C? So follow pathways. This is where that massive piece of pathways would come in useful. So if you start with essential, if I go this pathway by adding ammonia, I'll get this. If I go this way by adding hydroxy, I'll get an alcohol. So learn and get that massive pathways map done, please. The last few slides is simply telling you about the resources out there. Just to remind you, the knowledge organisers for 4.8 are particularly good, so please use it. And then try varying your revision. As I said last time I presented, so 2 weeks ago, I encourage my pupils to use things like Quizlet. Vary your revision. It is a challenging unit, is unit 4, so please just vary it. Make it as interesting for yourself as you possibly can. And that's it from me.